Hello everyone, and welcome to our new CloudNetX course. In this lesson, we'll explore the key elements that make up modern network design. Let's start with the Open Systems Interconnection Model. The OSI model is like a blueprint for how data travels across a network. It's broken into 7 layers, each with a specific role. At the bottom, the physical layer deals with the actual hardware, like cables and switches. Moving up, the data link layer manages how data is transferred between devices on the same network. The network layer handles IP addressing and routing, while the transport layer ensures reliable communication using protocols like TCP for error check delivery or UDP for faster connectionless transfers. The session layer keeps communication organized by managing sessions between devices. The presentation layer ensures data is in the correct format and handles encryption. Finally, the application layer is where users interact with services like email or web browsing. Now, let's dive into IP addressing, which is fundamental to network design. Every device needs an IP address to communicate, and we use either IPv4 or IPv6. IPv4, with its 32-bit addresses, is still widely used but has limitations in available addresses. That's where IPv6 comes in. With a 128-bit address space, IPv6 can support a nearly unlimited number of devices. But what if you're running out of public IP addresses? That's where Network Address Translation, or NAT, comes in. NAT allows multiple devices on a private network to share a single public IP address, conserving the address space. There are different types of NAT, including static NAT, which maps one private IP to one public IP, and dynamic NAT, which allocates addresses from a pool. Port address translation is the most common form, mapping multiple devices to one public IP using unique ports. Now, let's talk about networking protocols, the rules that allow devices to communicate. First, we have TCP and UDP, the two main transport protocols. TCP is reliable, ensuring that all data is delivered correctly, which makes it perfect for applications like file transfers and email. UDP, on the other hand, is faster but doesn't guarantee delivery, making it ideal for real-time applications like video streaming or online gaming. For routing, we rely on dynamic and static protocols. Dynamic protocols, like Open Shortest Path First and Border Gateway Protocol, automatically update routes based on network changes. OSPF is great for internal networks, calculating the shortest path between nodes, while BGP is the backbone of the internet, handling routing between large networks. Static routing, on the other hand, is manually configured and works well for smaller, simpler networks where paths rarely change. Let's move to Dynamic Host Configuration Protocol, DHCP, which makes IP address management a breeze. Instead of assigning addresses manually, DHCP automatically assigns IPs, subnet masks, and other configurations. This is especially useful in environments with lots of devices, like corporate offices or schools, where managing addresses manually would be overwhelming. Next, we have Network Time Protocol, or NTP. Accurate time synchronization is vital for logging, auditing, and coordinating systems across a network. NTP ensures that all devices in the network are operating on the same time, which is particularly critical in industries like finance, where precise timestamps can make or break compliance. Lastly, let's talk about the Domain Name System, or DNS. DNS translates user-friendly domain names, like www.example.com, into IP addresses that computers use to locate resources. Without DNS, we'd all be typing in long strings of numbers to access websites. It's a foundational service that keeps the internet user-friendly and functional. So, how do these concepts tie into network design? Let's consider an example. Imagine you're designing a network for a growing business. You'll need to decide whether to use IPv4 or IPv6 based on the number of devices and future expansion plans. You might implement NAT to maximize the use of limited IPv4 addresses while keeping internal IPs private. For routing, you might choose OSPF for its adaptability within a dynamic internal network, or BGP if you're connecting to external networks. DHCP will simplify IP management, while NTP ensures all your systems are synchronized. And of course, DNS will make accessing resources intuitive for users. In conclusion, designing a network isn't just about connecting devices. It's about ensuring that every piece works seamlessly together to meet the organization's needs. Thank you for joining us today, and see you soon.